students. So let me welcome you all to my 6th video on the chapter surface chemistry. In the 5th video, we started the discussion on properties of colloids, wherein we discussed colligative properties of colloids, optical properties of colloids, and also kinetic properties of colloids. Under kinetic properties of colloids, we discussed Brownian moment, random zigzag continuous movement of dispersed phase particles in dispersion medium is called Brownian moment. We discussed the cause for the Brownian moment in colloidal solutions and also the significance of Brownian moment. As we discussed, Brownian moment leads to stability of the colloids, is it not? Brownian moment leads to stability of the colloids. At the same time, as far as Brownian moment is concerned, Brownian moment is independent of nature of the colloids. One more important aspect that you need to know, that is Brownian moment is independent of nature of colloids. It doesn't depend on, as it is nature of the colloids. Irrespective of nature of colloids, all colloids will exhibit the phenomenon called Brownian moment. At the same time, this Brownian moment depends on size of the colloidal particles. Size of colloidal particles. Brownian moment depends on size of colloidal particles and also viscosity of the colloidal solution. That is, Brownian moment depends on viscosity of colloidal solutions, right? So these are the two important factors that you need to remember as far as Brownian moment is concerned. As you know that smaller the size of the colloidal particles, lesser the viscosity of colloidal solution, faster will be the movement of colloidal particles in dispersion medium. That is, as the size of the colloidal particles decreases, the movement of the colloidal particles will be increased. Similarly, as the viscosity of colloidal solution decreases, the movement of the colloidal particles will be increased. Is it not? That means smaller the size of the colloidal particles, lesser the viscosity of colloidal solution, faster will be the movement of the colloidal particles. So that is what we call it as the factors affecting on Brownian moment, right? Now this moment, we'll come to the one more important property of colloids that we need to discuss under the properties of colloids. It will be electrical properties of colloids. And as far as the colloidal particles in colloidal solution are concerned, these colloidal particles carry either positive charges or negative charges. That is, the colloidal particles in dispersion medium carry either positive or negative charges. All colloidal particles in dispersion medium carry same charges, but equal and opposite charges will be present in dispersion medium. All colloidal particles in colloidal solution carry same charges. It may be positive charge or it may be negative charge. But equal and opposite charge will be present in, yes, it is dispersion medium. That is the nature of the colloidal solution, is it not? For example, if I take, that is ferric hydroxide salt. Look at this, ferric hydroxide salt. This is one of the salts that we prepared by peptidization of ferric hydroxide precipitate in presence of ferric chloride peptizing agent. This is positively charged salt. Okay, na? This is positively charged salt. All ferric hydroxide colloidal particles will be characterized by positive charges. Okay, na? Due to the adsorption of Fe3 plus ions on the surface of ferric hydroxide. That's why all ferric hydroxide colloidal particles carry positive charges, but equal and opposite charges will be present in dispersion medium. That means dispersion medium will be characterized by negative charges. Dispersion medium will be characterized by negative charge. Similarly, just remember silver iodide salt that we prepared by peptidization of silver iodide precipitate using potassium iodide as peptizing agent. We prepared this, is it not? In this case, silver iodide salt particles carry negative charges due to the adsorption of I- ions, and therefore dispersion medium in the case of silver iodide salt will carry positive charge. That means all colloidal particles are carry, yes, it is same charges. All colloidal particles in colloidal solution carry same charges, but equal and opposite charges will be present in dispersion medium. So this is the observation as far as the electrical properties of colloidal solutions are concerned, right? And of course, based on the charge possessed by the colloidal particles, colloidal solutions can be classified into two types. One, it will be positively charged salts. Or you can say positively charged colloids. Second, it will be, as usual, negatively charged salts, or you can say negatively charged colloids, depending upon the charge possessed by the colloidal particles in colloidal solutions. As far as positively charged salts are concerned, these are the colloids which contain positively charged colloidal particles. The colloids which contain positively charged colloidal particles are called positively charged colloids, or you can say that positively charged salts, or you can say the colloids which contain positively charged dispersive phase particles. Colloids which contain positively charged dispersive phase particles, they are called as, yes, it is positively charged salts. Example for the positively charged salts will be, one, it will be hydrated, metal oxides. One type of colloids, it will be hydrated metal oxides, like hydrated ferric oxide, hydrated aluminum oxide, yes, and hydrated oxide of chromium, that is CrO3xH2O. These are the examples for positively charged colloids. Okay, now, apart from that, we can have some more examples like basic dyes. That is, dyes are colored organic compounds, right, which carry basic groups. In organic chemistry, the groups like NH2 group or the NHR groups, these are all examples for basic groups. Basic dyes are characterized by basic organic functional groups, right? That is, examples for the basic dyes will be methylene blue sol. The sol of methylene blue is characterized by positively charged dispersive phase particles. Because of that, methylene blue sol is an example for positively charged sol. Apart from that, I'll give some more examples like blood. Blood contains hemoglobin, right? Is an example for, yes, it is positively charged sol. Or you can say metal oxides like, yes, it is TiO2 sol. The sol of titanium oxide is also an example for positively charged sol. Like that, in all these cases, the dispersive phase particles will be characterized by positive charges. All dispersive phase particles of TiO2 in TiO2 sol will be characterized by positive charges. And dispersion medium will carry equal and opposite charge. Okay, na? So this is what we call it as examples for the positively charged salts. Like that, we have negatively charged salts. Negatively charged salts are the colloidal solutions which contain negatively charged colloidal particles. Or I can say negatively charged salts are the colloidal solutions. Negatively charged salts are colloidal solutions which contain negatively charged dispersive phase particles. Negatively charged dispersive phase particles in dispersion medium. Since dispersive phase particles carry negative charges, the dispersion medium will carry equal and opposite charge. That is, dispersion medium will carry positive charges. Like that, the colloidal solutions which contain negatively charged salt particles. The colloidal solutions which contain negatively charged colloidal particles are called as, yes, it is negatively charged salts. Example, I'll give some examples like, metal salts. For example, gold salt, platinum salt, or the silver salt. These are all the examples for, yes, it is negatively charged salts. Like that, we have metal sulfide salts. Metal sulfide salts, right? Example, we have arsenic sulfide salt, that is As2S3 salt, antimony sulfide salt, Sp2S3 salt, cadmium sulfide salt, okay na? Cadmium sulfide salt. These are all the examples for metal sulfide salts. All these metal sulfide salts carry negatively charged dispersive phase particles. Naturally, dispersion medium will carry positive charge, right? Similarly, I'll give some more examples for the negatively charged salts, like acidic dyes. Acidic dyes, they are the colored organic compounds containing acidic groups like COOH group. They are called as acidic groups, that is acidic dyes. For example, salts of eosin, salts of eosin, and of course salts of congorate. These are the examples for acidic dyes, and they are negatively charged salts. In these cases, colloidal particles carry negative charges. Similarly, we have solution of starch. Solution of starch is an example for negatively charged salt. Gelatin is an example for negatively charged salt. Or I can say gum, or I can say glue is an example for negatively charged salt. Or I can say a salt of clay, that is the salt prepared by using clay. Salt prepared by using clay. That is also an example for negatively charged salt. Or I can say the salt of charcoal is an example for, these are all the examples for, negatively charged salts. Like that, the dispersive phase particles in colloidal solutions will be characterized by either positive charge or negative charges. What I said, equal and opposite charges will be present in dispersion medium. So this is what we call it as the classification of colloids based on the charge possessed by the colloidal particles. Is it not? And of course, naturally, one question rises in your mind. How and why these charges are created over the colloidal particles? How and why colloidal particles acquire positive or negative charges over them? So this is the next important question. And in order to get the answer for that, we have some reasons. I'm going to list out some reasons based on different theories in order to account for the origin of the charges on colloidal particles. Okay, now let us see the next discussion. It will be origin of charges on colloidal particles. That is next and the important discussion as far as the electrical properties of colloids are concerned, right? We'll see that. Yes. Origin of charges on colloidal particles. Colloidal particles. Origin of charges on colloidal particles, that is the next discussion. Yes, origin of charges on salt particles. And of course, I can list out different reasons in order to account for the origin of charges on colloidal particles. One reason is, electron capture. One reason is electron capture by salt particles, colloidal particles, electron capture by salt particles, okay na? During their preparation by electrodispersion methods. During their preparation by electrodispersion methods. We have one of the methods for the preparation of colloids, that is electrodispersion method. You studied that under the headline Briggs electric arc method. Briggs electric arc method. Colloidal solution will be prepared by striking two electrodes. And during their preparation by electrodispersion method, salt particles may capture electrons from electrodes. Thereby, they possess charges. This is one of the reasons for the existence of charges on the surface of colloidal particles. That is electron capture by salt particles during their preparation by electrodispersion method. Briggs electric arc method. Okay, na? One of the electrodispersion method. And of course, as far as second reason is concerned, second reason is of course due to the preferential adsorption of ions. That is, second reason is preferential adsorption of ions from colloidal solutions. Preferential adsorption of ions from colloidal solution by colloidal particles. This is one more reason I can list out as far as origin of charges in the colloidal particles is concerned. Or I can say this can also be stated as due to the, yes it is, formulation of electrical double layer. That we'll discuss later, okay now? Due to the formation of, yes it is, electrical double layer on colloidal particles. This is also one more reason that I can quote as far as the origin of charges in the colloidal particles is concerned. And as far as third reason is concerned, that is ionization of surface molecules. Third reason is charge possessed by the colloidal particles may be due to the ionization of surface molecules. Due to the ionization of surface molecules, okay, na? Especially in the case of soap salts. Especially in the case of soap salts. Just remember that formation of mechanism of micelle formation by soap molecules. During micelle formation, the polar heads of the soap molecules, they were pointing towards the, yes it is, surface of the micelle, and non-polar tails will be pointing towards the center of the micelle. Okay? And that is due to the ionization of the surface molecules, that is, some colloidal particles may carry charges. Okay, now? So these are the three reasons I can quote as far as origin of charges over the colloidal particles in colloidal solution is concerned. Among these reasons, most accepted reason for the origin of charges on the colloidal particles will be, and that is due to the preferential adsorption of ions from the colloidal solution by colloidal particles. This is the most accepted reason as far as the origin of charges in the colloidal particles is concerned. And of course, we are supposed to study the detailed aspect of the origin of charges on the colloidal particles by preferential adsorption of ions from colloidal solution. So that is the next discussion. We'll see that the detailed aspect of the preferential adsorption of ions from the solution by colloidal particles. Okay, now that is the reason for the origin of charges over the dispersive phase particles in dispersion medium. Now let us see, as I said, that is among the reasons available for the origin of charges over the colloidal particles, most accepted reason is preferential adsorption of ions. Okay, now maybe positive or negative ions on the colloidal particles. Just remember, if negatively charged ions are adsorbed on the surface of colloidal particles, that results in the formation of negatively charged colloidal particles. If positive ion is adsorbed on the surface of colloidal particles, that results in the formation of, the positively charged salt. That means if two or more ions present in a colloidal solution, that is preferential adsorption of ion common to the colloidal particles takes place, and that leads to the origin of charges over the colloidal particles. So we'll see that particular aspect by taking certain examples. For example, look here. Just imagine, if I add, a dilute solution of, dilute solution of silver nitrate. Let me add dilute solution of silver nitrate to the potassium iodide solution. A dilute solution of potassium iodide. Yes. And then I'm going to take a silver nitrate solution, and that will be added to the potassium iodide solution taken in beaker. This is a beaker. Yes. This beaker contains what we call it as K plus ions and I minus ions. To this dilute solution of potassium iodide, if I add silver nitrate, I'm adding silver nitrate. Okay, na? Silver nitrate contains, silver ions and nitrate ions. And this silver nitrate, yes, that reacts with the silver iodide, that reacts with potassium iodide. The added silver nitrate reacts with potassium iodide in the beaker. That results in the formation of silver iodide precipitate. Yes. Now, in the beaker, we have silver iodide precipitate. And look at the solution of potassium iodide that contains K plus and I minus ions. To this particular precipitate, silver iodide, which is common ion, I minus is common to the silver iodide particle. Because of that, what happens, silver iodide particles. This is silver iodide particle. This will be surrounded by I minus ions. Okay, na? This will be surrounded by I minus ions due to the adsorption of common ion over the surface of yes, it is silver iodide precipitate, and that results in the formation of negatively charged silver iodide salt. That results in the formation of negatively charged silver iodide salt. This is the preferential adsorption of ions common to the yes, it is the ions present in the colloidal particles. That results in the formation of yes, it is the origin of charges over the surface of colloidal particles. Due to the adsorption of these ions, a layer of negative charges will be created on the surface of silver iodide. So this is how a layer of positive or negative charges will be formed on the surface of colloidal particles. That results in origin of charges over the surface of colloidal particles. Okay, na? Similarly, if I add potassium iodide solution to the silver nitrate solution taken in, yes, it is a beaker. I'm going to take a dilute solution of silver nitrate in the beaker. To this, I'm going to add potassium iodide. Yes, same reaction takes place. That results in the formation of silver iodide in the beaker. Now, in the silver iodide, this silver iodide in the beaker, this silver iodide in the beaker is in contact with Ag plus ions and NO3 minus ions. But for this precipitate silver iodide, which is common, Ag plus ions are common. Therefore, Ag plus ions will be adsorbed. Ag plus ions will be adsorbed on the surface of silver iodide. Ag plus ions will be adsorbed on the surface of silver iodide. That results in the formation of positively charged silver iodide salt. Just observe the method of preparation of silver iodide salt. If I prepare silver iodide salt by adding silver nitrate solution to the potassium iodide solution taken in beaker, then there is adsorption of negative ions on the surface of silver iodide that leads to the formation of negatively charged silver iodide salt. Here in this case, this silver iodide salt is prepared by adding potassium iodide to the silver nitrate solution taken in beaker. That results in adsorption of Ag plus ions over the surface of silver iodide. And of course, there is a layer of positive charges around the silver iodide particle, and that leads to the origin of charges over the surface of colloidal particles. On the basis of these examples, what I can conclude at this moment, the origin of charges over the surface of colloidal particles is due to the adsorption of ion common to the colloidal particles on the surface of colloids. So like that, one of the reasons for the origin of charges on the colloidal particles, it would be preferential adsorption of ions common to the colloidal particles in colloidal solution. So, and of course, I'll give some more examples. Just imagine if I prepare hydrated ferric oxide salt, right? That is, if I prepare hydrated ferric oxide salt, yes, this is hydrated ferric oxide salt. If it is prepared by adding ferric chloride, if I add this ferric chloride to the hot water, that results in the formation of hydrated ferric oxide, over which ferric ions will be adsorbed. That leads to, yes, it is positively charged hydrated ferric hydroxide salt, and that positive charge over the hydrated ferric oxide is due to the adsorption of common ion from the ferric chloride solution. And that is what we call it as the positively charged hydrated ferric oxide is formed when ferric chloride is added to the hot water there. Similarly, negatively charged hydrated ferric oxide is formed. When same ferric chloride is added to the sodium hydroxide solution. Adsorption of OH minus ions on the surface of hydrated ferric oxide takes place. That results in the formation of negatively charged salt. Hydrated ferric oxide. If this salt is prepared by adding ferric chloride to the hot water, that results in the adsorption of ferric ions. That leads to positively charged hydrated ferric hydroxide salt. Okay, na? So like that, that is preferential adsorption of ions common to the colloidal particles is one of the important causes for the existence of the charges over the surface of colloidal particles. So this is what we call it as the origin of charges over the, yes, it is the colloidal particles. Agbodalla? Yes, so this is what we call it as the one reason there. Yes, and of course, now at this moment, we'll go to the next discussion, and very important as far as your syllabus is concerned, it will be, yes, it is the formation of electrical double layer. Yes, so this is the next discussion, that is electrical double layer. That is one more important concept. Yes, now let us see the next discussion. It will be electrical double layer. Yes, as you know that a layer of positive or negative charges will be formed on the surface of colloidal particles due to the adsorption of ions on the surface of colloidal particles. Here it is. This is silver iodide salt, in which we have a layer of negative charges due to the adsorption of I minus ions on the surface of silver iodide particles. Or that this is silver iodide salt. Now I can represent like this: Ag bar I minus ions are adsorbed on the surface of, yes, it is silver iodide particles. And this layer of negative charges over the surface of colloidal particles is going to attract oppositely charged ions from the dispersion medium. Look at this. This layer of negative ions on the surface of silver iodide attracts the counter ions from dispersion medium. Counter ions from dispersion medium, that results in the formation of one more layer of opposite charges around the first layer. Look at this. This is a silver iodide salt that can be represented as Ag I bar Ag plus, because this is a positively charged silver iodide formed by the adsorption of Ag plus ions on the surface of silver iodide particle. This layer of positive charges on the silver iodide attracts the counter ions, that is negatively charged ions from dispersion medium. And this is a layer of counter ions around the first layer. And this is what we call it as second layer. We call it as this is a second layer of counter ions from the dispersion medium. And this combination of yes, it is two layers of opposite charges around colloidal particles is called electrical double layer or Helmholtz electrical double layer. The combination of two layers of opposite charges around the colloidal particles is called Helmholtz electrical double layer. Of course, in the colloidal solution, just observe the first layer of ions. The first layer of ions around the colloidal particle is strongly attached to the surface of colloidal particles. The first layer of ions around the colloidal particles will be strongly attached to the colloidal particles. And this layer that is strongly attached to the surface of colloidal particles is called fixed layer. Whereas the second layer of counter ions, which is mobile, it is due to the counter ions from the dispersion medium. And this second layer is mobile and it is known as diffused layer. Just observe here, layer of positive charges, first layer of positive charges due to the adsorption of Ag plus ions on the surface of colloidal particle, that constitutes fixed layer of charges. Second layer is a layer of counter ions from dispersion medium, which is mobile layer, is it not? This is a mobile layer. And this, yes, it is a combination of two layers around the colloidal particles is called electrical double layer. And due to the presence of two layers of opposite charges around the colloidal particles, there exists a development of some sort of potential difference between two layers of opposite charges. That potential difference between the fixed layer and mobile layer of opposite charges is called electrokinetic potential. Electrokinetic potential, or you can say this is also called as Zeta potential. It's also called as Zeta potential. That is, Zeta potential refers to the potential difference between a fixed layer of charges around the colloidal particles and diffused layer of opposite charges, and that is what we call it as Zeta potential. And of course, the existence of the similar charges has got its own importance. Existence of charges over the colloidal particles, and also that Zeta potential has got its own importance as far as the stability of colloids is concerned. That is, the existence of similar charges over the colloidal particles results in stability of the colloidal particles. Because just imagine if a layer of similar charges are formed on the surface of all colloidal particles, what happens? the colloidal particles undergo mutual repulsion. If all colloidal particles are characterized by similar charges on their surfaces, there is a force of repulsion among the colloidal particles that prevents aggregation of colloidal particles. If aggregation of colloidal particles is prevented, naturally colloidal particles will remain suspended in dispersion medium, and thereby that imparts stability to the colloidal particles. What I said, as far as stability to colloidal solutions is concerned, the colloidal solution is said to be stable as long as dispersed phase particles remain suspended in dispersion medium. If all the colloidal particles in dispersion medium are settled down under the influence of gravitational force, then colloidal solution is said to be destabilized. That you should keep it in mind. Okay, now just imagine if I add excess electrolytes to the colloidal solution, the charges over the dispersed phase particles will be neutralized. Thereby, that is zeta potential and the repulsive forces among the colloidal particles will be decreased when excess electrolyte is added to the colloidal solution. The charges over the colloidal particles will be completely neutralized due to the presence of ions in the electrolytic solution. And at the same time, the repulsive forces between the colloidal particles will be decreased. That results in aggregation of colloidal particles. Once the aggregation of colloidal particles takes place, size of the colloidal particles increases. And that results in precipitation of colloidal particle under the influence of gravitational force. So thereby destabilization of colloidal solution takes place. That's why I said, that is the removal of excess electrolytes from the colloidal solutions is very, very essential. While discussing dialysis, I used to say that the excess electrolytes present in colloidal solutions has to be removed. Otherwise, destabilization of colloidal solution takes place. I think you got the reason for that. Okay, now let us see. Next discussion it will be, yes, it is electrophoresis. We'll see that. Yes. So let us see one more important phenomenon under electrical properties of colloids. It will be electrophoresis. This is one phenomenon that I can make use of in order to identify the nature of charges over the colloidal particles. That is, you can determine whether the colloidal particles carry positive charges on their surfaces or negative charges on their surfaces. You can easily identify the nature of charges over the colloidal particles by using this particular phenomenon called electrophoresis. That is, as far as the electrophoresis is concerned, the phenomenon in which the colloidal particles will move towards cathode or anode in presence of electric field, and that is what we call it as electrophoresis. The moment of dispersed phase particles towards anode or cathode in presence of electric field, so that is what we call it as electrophoresis. Just observe, in order to carry out this phenomenon electrophoresis, I can make use of this simple experimental arrangement. This experimental arrangement consists of what? U-shaped glass tube. This particular glass tube is fitted with two electrodes. Two platinum electrodes are fitted to the, yes, it is U-shaped glass tube in which colloidal solution is taken. Just imagine if I fill this U-shaped glass tube, with negatively charged colloidal solution, in presence of electric field, if I apply electric field through the solution of colloid, what happens? Look at this, negatively charged dispersed phase particles, they are moving towards a positive electrode. Negatively charged dispersed phase particles are moving towards, yes, it is positive electrode, anode. Just observe, the colloidal particles are going to be concentrated around the positive electrode of this particular U-tube. If this particular U-tube, this particular U-shaped glass tube, if it is filled with positively charged colloidal solution, what happens? The colloidal particles will be moving towards cathode. That is, the colloidal particles will be moving towards oppositely charged electrodes in presence of electric field, and the phenomenon is called as electrophoresis. If colloidal particles are moving towards anode, naturally colloidal particles must carry negative charges. If the colloidal particles are moving towards cathode, generally the colloidal particles must carry positive charge. Because of that, I said I can make use of this particular phenomenon in order to confirm the nature of charges over the colloidal particles. So by any means, if you stop the movement of dispersed phase particles, by any means, by any method, if you stop the movement of dispersed phase particles, then there is a movement of dispersion medium towards the anode or cathode. There is a movement of dispersion medium towards the anode or cathode, and that phenomenon is called as electroosmosis. That phenomenon is called as electroosmosis, right? That is electroosmosis is what we call it as movement of dispersion medium in presence of electric field. Even dispersion medium is characterized by equal and opposite charges, because of that, in presence of electric field, even the molecules of dispersion medium will be moving. And the phenomenon is called electroosmosis. Now at this moment, we'll go to the next and the important discussion. As per our NCERT textbook is concerned, it will be, yes, it is the coagulation of colloids. We'll see that coagulation of colloids, or you can say flocculation of colloids, or you can say precipitation of colloids, right? We'll see that, yes. Let us see one more discussion under properties of colloids. It will be coagulation of colloids, flocculation of colloids, or precipitation of colloids. Colloids are characterized by similar charges over the particles of colloids will be characterized by similar charges over their surfaces. And the existence of similar charges over the colloidal particles results in repulsive forces among the colloidal particles, and that repulsive forces among the colloidal particles prevents aggregation of colloidal particles. If the aggregation of colloidal particles is prevented, the colloidal particles will remain suspended in dispersion medium that imparts stability to the colloidal system. Just imagine, if the layer of charges over the colloidal particles is removed, by neutralizing their charges, then what happens, the repulsive forces among the colloidal particles will be decreased. The repulsive forces among the colloidal particles will be decreased. That results in mutual attraction among the colloidal particles. That leads to aggregation of colloidal particles. If aggregation of colloidal particles takes place, size of the colloidal particle increases. Those bigger particles will coming into the influence of gravitational force, and thereby settling of colloidal particle takes place. And that process of settling of colloidal particles by neutralization of their charges is called coagulation or flocculation of colloids. That process of settling of colloidal particles by neutralization of their charges is called coagulation or flocculation of colloids. And of course, totally, I can bring about, that is settling of colloidal particles by neutralizing the charges present on the surface of colloidal particles. And of course, in order to bring about coagulation of colloids, I have some methods. In order to neutralize the charges over the colloidal particles, I can go for some methods so that I can bring about the coagulation of colloids. Let me list out some methods which I can use in order to bring about coagulation of colloids or flocculation of colloids. We'll see that one by one. First of all, it is by electrophoresis. This is one of the methods with which one can bring about coagulation of colloids. Electrophoresis. Electrophoresis refers to the movement of dispersed phase particles towards cathode or anode in presence of electric field. Just imagine, upon passing electricity, what happens? The colloidal particles will be moving towards oppositely charged electrodes. Thereby, they lose their charges over the oppositely charged electrodes, and that results in aggregation of colloidal particles. And finally, colloidal particles will be settled down. That is one method. Second is, of course, by mutual coagulation. Second method is by mutual coagulation, or you can say by mixing two oppositely charged salts. That is, coagulation can be brought about by mixing two oppositely charged salts. When two oppositely charged salts are mixed in equal proportions, then what happens? The neutralization of charges over the colloidal particle takes place. Once the neutralization takes place, naturally precipitation takes place, or you can say that coagulation takes place. For example, if I mix positively charged hydrated ferric oxide salt, positively charged hydrated ferric oxide salt with negatively charged arsenium sulfide salt. Look at this. This is arsenium sulfide salt. This is negatively charged salt. When it is mixed with positively charged salt like hydrated ferric oxide, naturally what happens? These are the two colloidal solutions of opposite charges. What happens? Neutralization of charges over the colloidal particle takes place upon mixing. Thereby, coagulation takes place. Totally, by any means, if you neutralize the charges over the colloidal particles, that results in coagulation. That results in settling of colloidal particles under the influence of gravitational force. And that is what we call it as coagulation. And of course, the third method for the, yes, it is coagulation of colloids, it will be by boiling. By boiling also, one can bring about coagulation of colloids. Just remember, when egg is boiled, coagulation of proteins, egg albumin present in the egg takes place, and that is an example for coagulation. Boiling of egg is an example for coagulation, and that is by boiling you can bring about, yes, it is coagulation of colloids. On boiling, what happens? The layer of charges over the colloidal particles will be disturbed. A layer of similar charges over the colloidal particles will be disturbed due to the increased collision of dispersion medium molecules over the dispersed phase particles. Naturally, the charges over the surface of colloidal particles will be removed or disturbed, and that results in coagulation of colloids. That is, on boiling, that a layer of charges over the surface of colloidal particles will be disturbed due to the increased collision of dispersion medium molecules on the dispersed phase particles, and that disturbance of charges over the surface of colloidal particles results in aggregation of particles. If aggregation of particle takes place, that results in coagulation of particles. So this is the third method for the coagulation of colloids. As far as fourth method is concerned, that is by persistent dialysis. That is by persistent dialysis. This is another method for the coagulation of colloids. You know that dialysis involves removal of electrolytes from the colloidal solutions. Dialysis involves removal of electrolytes from the colloidal solution. That is, excess electrolytes present in colloidal solution will be removed by the phenomenon called, yes, it is dialysis. Remember, if there is a prolonged dialysis or repeated dialysis, what happens? The complete removal of electrolytes from the colloidal solution takes place. If all the electrolytes present in the colloidal solutions are completely removed, no ions will be left in the colloidal solution for the formation of a layer of charges on the colloidal particles. If all the ions present in the colloidal solution are removed, no ions will be left for the formation of layer on the colloidal particles. Then what happens? If there are no ions, no layer of charges on the surface of colloidal particles, and thereby aggregation of colloidal particle takes place, that results in coagulation of colloids. That's why I said, while discussing dialysis, that persistent dialysis of the colloidal solution is not permitted, because presence of small amount of electrolytes in the colloidal solution is very essential. Presence of small amount of electrolytes in colloidal solution is very essential. That imparts stability, because if small amount of electrolyte is present in colloidal solution, absorption of common ion on the surface of colloidal particle takes place. That results in the formation of layer of similar charges on all the colloidal particles. That imparts stability. If all the electrolytes present in the colloidal solutions are removed by persistent dialysis, repeated dialysis or prolonged dialysis, then coagulation of colloids takes place. Okay, na? So this is the fourth one. Persistent dialysis is another method for the coagulation of colloids. And of course, as far as fifth method is concerned, that coagulation can be brought about by the addition of electrolytes. The coagulation of, yes, it is, colloids can be brought about by addition of electrolytes. Look at this. Electrolytes are characterized by, yes, it is positive ions and negative ions, is it not? ಯಾವುದೇ electrolyte ತಗೊಂಡ್ರು ಕೂಡ ಅದರಲ್ಲಿ ಒಂದು ಪಾಸಿಟಿವ್ ion ಇರುತ್ತೆ, ಒಂದು ನೆಗೆಟಿವ್ ion ಇರುತ್ತೆ, ಹೌದು ತಾನೆ? Just imagine, if excess electrolytes are added to the colloidal solution, what happens? The ions from the electrolytes are going to neutralize the charges over the surface of colloidal particles. If the charges over the colloidal particles are neutralized, what happens? Aggregation of colloidal particle takes place. That results in coagulation of colloidal particles. That is, addition of excess electrolytes to the colloidal solutions leads to the coagulation of colloids. And of course, as far as electrolyte is concerned, as I said, electrolyte is characterized by positive ions and negative ions. And of course, generally, positive ion of electrolyte is going to bring about coagulation of negatively charged salt. Negative ion of electrolyte is going to bring about coagulation of positively charged salt. and that ion of the electrolyte responsible for the coagulation of a particular colloidal solution is called coagulating ion, or you can say that flacculating ion. That is the ion from the electrolyte responsible for the coagulation of a particular colloidal solution is called coagulating ion, or yes, it is flacculating ion. For example, if I take an electrolyte sodium chloride contains Na plus ions and Cl minus ions. So the Na plus ions will bring about coagulation of negatively charged salts. Cl minus ions will bring about coagulation of positively charged salts. That is the ion that is responsible for the coagulation of that is a particular salt is called as that is coagulating ion, or you can say that flacculating ion. Okay, now, and of course the ability of yes, it is coagulating ion to coagulate a particular colloidal solution depends on the charge possessed by the coagulating ion. That is the ability of yes, it is coagulating ion to bring about coagulation of particular colloidal solution depends on the charge possessed by the yes, it is coagulating ion. That can be understood by making use of one rule, what we call it as Hardy-Sulze rule. Yes, I can make use of this Hardy-Sulze rule in order to understand the ability of coagulating ion to bring about coagulation of a particular, yes, it is a colloidal solution. According to Hardy-Sulze rule, the ability of a coagulating ion to bring about coagulation of a colloidal solution is directly proportional to the charge possessed by the coagulating ion. For example, for coagulation of yes, it is negatively charged salt, for coagulation of negatively charged colloidal solution. Look here, that is the ability of coagulating that particular negatively charged salt, that is in the case of Na plus ion is less than that of yes, it is Ba2 plus ion. The ability of Na plus ion to bring about coagulation of negative salt is less than that of Ba2 plus ion. The ability of Ba2 plus ion to bring about coagulation of negative salt is less than that of yes, it is Al3 plus. That is, as the charge possessed by the coagulating ion increases, the ability to coagulate a particular salt increases, and that ability to coagulate a particular colloidal solution is called coagulating power. Therefore, as the charge possessed by the coagulating ion increases, coagulating power increases. Coagulating power increases. That's why now that is the coagulating power of Na plus ion will be less than Ba2 plus ion. Coagulating power of Ba2 plus ions will be less than coagulating power of Al3 plus ion. Similarly, for coagulation of yes, it is positive salt. For coagulation of positive salt, that is the coagulating power of Cl minus is less than SO4 minus. Coagulating power of SO4 minus will be less than, that is coagulating power of PO4 minus, that will be less than coagulating power of FeCN6 times yes, it is 4 minus. So this is what we call it as the ability of a coagulating ion to bring about coagulation of particular salt is directly proportional to the charge possessed by the coagulating ion. As the charge possessed by the coagulating ion increases, its ability to bring about coagulation increases. That is, greater the charge possessed by the coagulating ion, greater will be its power to bring about coagulation. Okay, na? And of course, if coagulating power increases, amount of electrolyte required to bring about coagulation of colloidal solution decreases. Just imagine the coagulating power of Al3 plus ion is very high compared to the coagulating power of Na plus. Because of that, I need a small amount of Al3 plus ions to bring about coagulation of negative salt compared to the amount of Na plus ion required to bring about coagulation of negative salt. Similarly, the coagulating power of ferrocyanide FeCN6 4 minus is very high. Because of its high coagulating power, amount of ferrocyanide ions required to bring about coagulation of positive salt is least compared to the amount of Cl minus ions required to bring about coagulation of positive salt. That means as the charge possessed by the coagulating ion increases, coagulating power increases, coagulation value decreases. What is coagulation value? Coagulation value is minimum concentration of electrolyte in millimoles per liter required to bring about coagulation of a particular colloidal solution in 2 hours, and that is called as coagulation value, or you can say flocculation value. And flocculation value refers to the amount of electrolyte in millimoles per liter. That is, you are supposed to express concentration of electrolytes in millimoles per liter. That is minimum concentration of electrolyte in millimoles per liter required to bring about coagulation of colloidal solution in 2 hours. So that is what we call it as the coagulation value. For example, if I say coagulation value of electrolyte A is 2 into 10 to the power minus 3 and think coagulation value of B is 3 into 10 to the power minus 4. Yes, it is. And of course, millimoles per liter. It will be in terms of millimoles per liter. Coagulation value of electrolyte is electrolyte A is 2 into 10 to the power minus 3. Coagulation value of electrolyte B is 3 into 10 to the power minus 4. Out of these two, which has got high coagulating power? Yes. And B will have high coagulating power because the amount of electrolyte B required to bring about coagulation of particular sol is less. 3 into 10 to the power minus 4 is less than 2 into 10 to the power minus 3. Therefore, coagulation value of B is less. Therefore, its coagulating power is more. So that is what we call it as Hardy-Sulzer rule. According to Hardy-Sulzer rule, the ability of coagulating ion to bring about coagulation of colloidal solution is directly proportional to the charge possessed by the coagulating ion. Greater the charge possessed by the coagulating ion, greater will be the coagulating power, lesser will be the amount of electrolyte required to bring about coagulation. So this is what we call it as, yes, it is the coagulation, and of course the phenomenon called coagulation, and of course coagulation value, or you can say flocculation value. Okay na? In the next video we'll see remaining aspects of the colloids. It will be, yes, it is coagulation of lyophilic colloids, okay na? Emulsions, and of course one more small discussion, it will be the colloids around us. These are the discussion that we'll see in the last video of the chapter surface chemistry. We'll see in the next video. Okay na? Thank you, right?